Good morning, class. Welcome back to lecture 9.1, where what we're going to do is we're going to explore a scenario which is going to be Everest. Okay, so we're going to do this in two parts, lecture 9.1 and 9.2. In 9.2, we're going to actually derive something called the adiabatic lapse rate, which we'll discuss. And then we're going to go to the live class, and we will do a pretty extensive example. It'll take us probably half or more of the class to work out in class about the work and the heat done in PV diagrams and going through loops. Okay? So let's start today with our example of Everest. Okay, and I really mean Mount Everest. Okay, so this scenario is going to give us it's partly an example, but really it's more a chance for us to work through some methodology for exploring a new topic. Okay. All right. So last time we talked about adiabats and the work along an adiabat. And so this time it's going to sort of pick up with that. This at 9.2, the adiabats again. Okay, so let's stick with 9.1. Let's start on asking the question: what are the pressure, temperature, and density, right? The air density on top of Mount Everest. All right. So, do we have the tools to explore such questions? The answer is yeah, we're pretty close. So the first thing we need to know is that Everest, its altitude, which we're going to describe as h, right? This is going to be our altitude, is 8,840 meters above sea level. Okay? That's right, above sea level. Which we're going to call H0 equals 0. Okay, remember that at sea level, P0 we called it, is the pressure of the atmosphere at sea level was 1.013 times 10 to the 5 pascals. Okay? Okay, so how are we going to do such a thing? Okay. So let's start by calculating the pressure on the top of Everest, right? Assume that the atmosphere is a uniform density. Okay, so we're obviously sure that this isn't going to be true in the end, right? But in physics, it's often to approach a complicated problem, it's good to start with the simplifying assumptions and then refine further. Okay, so let's calculate what that density might be. Okay, So remember that the density, rho, is the mass over the volume. And I'm going to rewrite this as the molar mass. So the molar mass is going to be little m times n over v. All right, where little m is the molar mass. Let's also assume that it's an ideal gas, which is actually quite accurate. Okay, so now we see we have an n over v. So we're getting pretty good at thinking about ideal gases. So we know we should always probably write down our ideal gas law, PV equals nRT. And we can rewrite n over v then as P over RT, right? So our density is going to be our little mass, our molar mass, times P over RT. Okay. So we're just calculating what that uniform density is. So do we know these numbers? Well, at sea level, right? So at sea level, we had P was equal to P0, and T was 300 Kelvin, let's say. What's the molar mass of air? Well, actually, what's the dominant component of air? So air is like 75% nitrogen, some percentage oxygen, right? So if you have to guess, right? Just guess so you think, okay, nitrogen, gaseous nitrogen is N2. That's atomic number 7, right? Which means that so for nitrogen, it's simple enough in the periodic table that there's 7 protons and 7 neutrons, right? So for nitrogen, the molar mass should be about 28, right? So that's 4. So 7 times 2 is so 7 protons, 7 neutrons. That's 14, but this is N2, so you double it, right? So it's 28 grams per mole, okay, approximately. Turns out that's a pretty good guess for air. It's 29 grams per mole. Or remember, we're not, while grams are our metric, they're not our SI unit. We want to switch that to kilograms. So 0.029 kilograms per mole. Okay, so now we can calculate that density. This is 0.029 kilograms per mole times 1.013 times 10 to the 5 over R is 8.314. We derived that recently. Joules per mole K times the temperature 300. Let's make sure our units work out. Probably should have just kept them around. So this is kilograms per mole. Kilograms per mole. This one was pascals, which was newtons per meter squared, over joules per mole K times K. All right, so these kelvins cancel out, right? So we've got our moles. This mole is going to come to the top. So our moles are going to cancel out. A joule is a newton times a meter, right? So now we are at kilogram we have newtons, newtons up times meter, so that's kilogram meter cubed. Great, that's what we expect for a density. So our answer was 1 point, calculate it out, 1.8 kilograms per meter cubed. Okay, when we have the density, now we can calculate the pressure. So the pressure on the top of Everest is simply going to be the pressure at sea level minus rho GH. And I've got a minus sign because we're going up in altitude. I believe in the first lecture we had maybe a positive and we had measured negative. Okay, so let's go ahead and figure out what that is. So now we have 1.013 times 10 to the 5. We have minus 1.18 times 9.81 times 8,840 meters. Okay. Calculate that out. Go ahead and actually pause if you want. Take a minute to work that out, just so you get some practice on these things. Make sure you understand your units. It's going to be 926 pascals. Sorry, minus 926 pascals. Right, remember at sea level, right, we have 101,300 pascals. So 100,000 pascals, and now we have minus 96. Two things, what the heck are we talking about with a minus? What does it mean to have a pressure less than 0? When we talked about scales of pressure, did we have any less than 0? No, we did not. Right? So, this would suggest, right, another way to say it is that the zero of pressure was at 1.013 times 10 to the 5 minus 1.18 times 9.81 times h. I believe that h was 8750. Meters. This would mean that the atmosphere stops, right? That the atmosphere would just stop at this pressure. 90 meters below the top of Everest. So we know that Everest has, low pressure, right? You can imagine, remember seeing videos of people with face masks, right? But gas masks for oxygen masks. But clearly this didn't work, right? So actually, let's go ahead and pause, and I'll erase the board, and then we will start again, and we will make our next assumption, which is, of course, that we'll allow the air to have non-uniform density, right? We know that instinctively there's less pressure, there's less density of the air. It's not just that the pressure goes down, it's that the density goes down. So let's go for 9.2. Let's actually work out now for a non-uniform density of the air what the pressure on the top of Everest would be.